So what we're going to be talking about today is kind of classifying data or looking at sets of numbers and really determining if it is, looking at data and seeing if it's considered exponential or not. And we could have quadratics or linear functions as well. Now, when we look at exponentials, and we'll actually just look at some random ones. Let's do 5 to the x. And this would be considered an exponential function because we have a base of 5 and the variable is in the exponent. So it's considered an exponential function. Now, if we look at the outputs that this function has, when x is 0, it has an output of 1. When x is 1, it has an output of 5. Then 25, 125, 625, 3125, 15,625, 78,125, and it continues on. But there is something interesting about each one of the outputs from one to the next to the next. What do we notice with these here? Yeah, so each time we have this multiplication of 5 from one to the next to the next. So with these exponentials, if we have a decently spaced range that the x values are not jumping, that we have a difference of 1, 2, it's not giving us random values, but as long as we have this nice pattern, it will have a common ratio for the outputs. And this doesn't work with just this one here, it actually works with any of them. So this one here is 5 to the x. Now we could do, say, 8 to the x. Here, well, we have 1, 8, 64, 512, 4,096, and again, it's still multiplying by 8 each and every single time. So if it's considered exponential, really we're going to have this common ratio between any of the y values for any of these here. Now, if it was just a quadratic, if we have a quadratic, and it's going to do this eventually, hopefully, and we look at its values, well, it's not the same multiplication because we have 1, 0, 1, 4, 9, 16, 25. It's increasing faster. There's not a common rate. But there is something interesting with this data here. Well, the difference between 0 and 1 is, well, 1. Difference between 1 and 4 is 3. 4 and 9 is 5. 9 and 16 is 7, 8, not 8, 7, 9. And it continues on in this way. But if we look at that difference, what's the difference between 1 and 3? 3 and 5. 5 and 7. 7 and 9 is. So with these quadratics, and it works out with any quadratic, if I look at the outputs and the difference of the difference is the same number, then it's actually considered to be a quadratic. So really any quadratic, no matter what it is, will operate in this way. And we actually get kind of a pattern for that. Because if the difference of just any set of numbers is the same, then it's considered to be linear, it's a line. Because a line is just increasing at a steady, constant rate. The difference of a difference will give us a quadratic. So if I were looking at a cubic, a degree 3, what would we think it would be? Well, the difference of the difference is quadratic, so cubic would be the difference of the third. So if we look at these here, well, 1, 7, and this would be 19, and then we have 3, 7, here's 1, 37, do one more, 61. Well, the difference between this here is 6, then we have 12, and this is 18, and then 24, and our difference is 6, 6. So for cubics, the difference of the difference of the difference, if we have those sets of numbers, will tell us that it's a cubic. And we can do the same for quintic or quartic. And it'll keep telling us that. And the reason that this is nice is because if I look at a set of numbers and they give us a set of numbers, let's see here, over here, like this here, and I'm trying to figure out what the function is or what kind of function we're going to use for this here, if I can tell how the outputs operate, I can have an idea what type of function we're looking for. So when we look at this here, trying to look at what's happening from one number to the next, y'all see any kind of pattern or something that's going on with the outputs? Multiplies by 2 from one to the next to the next. So what it has is a common ratio, that the ratio for many of these numbers is always going to be the same. And the way we can kind of look at ratios is take the new, so 1 over the old. So we can do 1 divided by 0.5, which actually works out to be 2. We can do the next one. 2 over 1 is 2. 4 over 2. 4 divided by 2 is 2. Then we'd have 8 over 4, which is 2. 16 over 8 is 2. And last but not least, 32 over 16 is 2. So if it has a common ratio, it has to be the same across all of them. And because it has a common ratio, this is actually considered an exponential. I don't know why I keep spelling it that way. It's an exponential function. I keep wanting to add an extra s. But that's it for this here. Any questions on this here?
So exponential is where it's just the very first difference to do.
Mm-hmm. Yes.
Can we go farther than cubic?
Not too much in here. So let's look at this one here. So we have 2, 0, 2, 8, 18, 32, 50. So do we think this one would be a exponential? Because we can check our common ratio. So 0 over 2 is, and then the next one would be 0, because 0 over 2, and then we'd have, not 0, it would be 2 over 0, and 2 divided by 0 is, because if we wanted to actually solve it, 2 divided by 0 is what? Well, we'd actually multiply both sides by 0, because this is the same as 2 is equal to x times 0. Well, what times 0 is 2? Well, anything times 0 is what? So can I ever multiply a number by 0 and get 2? No. So that's the main reason why we can't divide by 0. This is undefined. Because when we're dividing by 0, really you're saying what number times 0 equals something that's not 0. It just doesn't work. So this here does not have a common ratio. Because if it were, all of those should be the exact same thing. So let's look at here. Let's look at our differences. And the way that we can look at differences, if it's kind of hard to see between each number, we can go new minus old. So the first one would be 0 minus 2, which is negative 2. Then we do 2 minus 0, which is 8 minus 2 is 18 minus 8 is 32 minus 18. And 50 minus 32 is not 16. This here should be 18. Well, those aren't the same, so let's see what the difference of the difference is. 2 minus negative 2 is It's a negative and a negative make a positive. 6 minus 2 is? So we have a common difference of the difference, which means this is a quadratic. This is a quadratic function because the difference of the difference is the same. Questions on any of this here? How about this one here? What do we think? $243, 81, 27, 931. So I would agree there's a 3, so we could, because we can see this here, so 81 over 243. So we're multiplying each one by 1/3 is what it works out to be. Because we can do 27 over 81, which would reduce to 1/3. Then we'd have 9 over 27, which would be 1/3. 3 over 9 is 1/3. And last but not least, we have 1 over 3, which is just 1/3. So this here would be exponential. Any questions on any of these here so far? Is this one here going to be exponential? Probably not. Because probably by this point in the year, you've noticed that most of the time, if we have something other than what we're wanting, especially exponential, it always alternates or switches out. Yes? Looking at the outputs, is there another kind of hint that might be telling us that this is not exponential? That's fine. So the x is going by 2 is actually not going to change too much because it's at a constant difference. Because we're increasing it by 2 each time, so that's fine. But I'd really look at the y values because there's something specific about them that this has that kind of is giving us an inclination that this is not going to be exponential. A repeat of 13. Because when we talk about exponential functions, their graphs, when we looked at them, they either started low and went high, or they started high and went low, because they were either constantly increasing or constantly decreasing, yes? Now, we know about quadratics is that they came a U-shape. They went up and went down, or they're coming up and going down. They have this U-shaped type function. Let's see here. And, so, come on. 2 graph. So this there is an exponential, and there is a quadratic. So we're going this U, so we will have some repeat of the numbers. For an exponential, we will not. So we look at this here, because we have 13, 5, 13, it's making that kind of U shape we're repeating. So most likely this is going to be a quadratic or an even degree polynomial, because we'll see the same type pattern in 4th degree. 3rd degree can have some of this, but normally it's going to be a S kind of curve. It's going to go up, down, back up. Well, we can do 5 minus 13, which is -7. Let's see here, 8. Yep, -8. Trying to do math way too fast. Because the difference between 13 and 10 is 3. The difference between 10 and 5 is 5. 5 and 3 is 8. 5 and 13 would be 13 and 37. 37 and 77 is 40, and 77 and 133. 56. Well, our difference between -8 and 8 is 16. Well, we keep increasing by 16, yes? This is actually kind of a shortcut way to actually figure out the next one in the sequence. Because even though we could go about trying to find out what the actual calculations for this, but I know the difference of the difference has to be 16, yes? So whatever the difference of these next two should be 16. So I can do 56 plus 16, which would be 72. So the difference between these next two numbers is 72. So we can actually use the difference of the difference to find out what the next numbers in the sequence are without actually finding the equation. So if we know how to manipulate the numbers, we can actually get to answers a little bit quicker. Any questions on this here? So we'll look at these last two and then we'll move on to the next thing that we're going to cover. Determine the type of function represented by the table. Explain your reasoning. So we have, well, it's going by 10, then we have 15, 12, 9, 6. So we can look at the ratios, 12 over 15, 9 over 12, 3 over 9. Well, I do know not 3 over 9. 6 over 9 is going to be 2/3. 9 over 12 is 3/4. And this here is 3/5. Well, the common ratio is not the same across these. Maybe the common difference, or the common difference of the difference is. So the difference between 15 and 12 is 12 and 9. 9 and 6. Well, we already got a common difference between these, yes? Well, it's not going to be quadratic because quadratic is difference of the difference. So what would this be? It would not be exponential. Because quadratic was degree 2, two differences. So if we only have one difference, it's not quadratic, we're going down. We might have to line it out. We do. A line is linear. Because if it just has a common difference, it is considered to be linear. It's a linear function. I think so. Because if it's just a common difference, then it's linear, so degree 1. If there's no common difference, if all the y values are the same, it's considered a constant function. Constant function is degree 0. One difference, degree 1 is linear. Two differences is degree 2, which is quadratic. Three differences was degree 3, which is cubic. So it keeps increasing. It's a common ratio from one to the next. Because the quadratic or polynomials are not increasing at a constant rate. They're increasing faster and faster as the function gets bigger. Where exponentials, all the way across, 9 over 27, 3 over 9, and 1 over 3, for any of the numbers, we have this constant multiplication because we're just repeating that multiple. Because really, from one number to the next, we're multiplying it by this constant term. Because for our exponential functions, really, for this here, we're looking at 1/3 to the x. It's being multiplied by itself so many times. That's why we get this common ratio, this common pattern. Where linear, this here would be negative, because plus 15x negative 3/10, to where each number that we have, we're multiplying it by this negative 3/10, or we're going to end up getting a difference of 3 eventually. Does that kind of make sense how these numbers are working? Because normally we look at the functions, but we don't normally look at their outputs and how they work with each other. Now we're going to do a few of these here today. I think we're going to do at least 3 to 4, and then we'll finish this up tomorrow. Our general exponential function comes in the form of y equals a times b to the x. A times b to the x. And what we want to do is we want to find the general equation for this here. Now they give us 2 points to work with, 1/6 and 3/54. So when I have an x value of 1, the y value is 6, whatever values a and b are. When the x value is 3, the y value is 54. X and y, x and y. So what that tells me for 1/6, that when y is 6, x is 1. So a times b to the first, whatever a and b are, we get a value of 6. When x is 3, so y is 54 is equal to a b to the third. When I take a times b to the first, I get 6. When I take a times b to the third, I get 54. So both of these are true. Both of these are points on the line. I'll scroll back up. And we know that the values of a and b for both of these here are the exact same. Because if they're defining the same equation, those two values have to be the same. The only things that are really changing are x and y. Now what we're going to do to solve this is use substitution. You haven't used this in a while. We haven't talked about this probably since last semester. But we're going to substitute one equation into the other. Because I know the a's are the same and the b's are the same, we can do this here. So what I'm going to do is I'm going to take 6 equals ab to the first and divide both sides by b, which will tell me that a is equal to 6 over b. Now this might seem a little weird, but this is going to make sense once we actually do the next step. Because I do know that the a's are the same and the value of b is the same, yes? Well, now I have an equation over here. A is equal to 6 over b. So we can kind of see that how it's set up, yes? So what I can do is I can take this 6 over b and plug it in for a, because I said a is equal to 6 over b, yes? So that means over here, 54 is equal to 6 over b times b to the third. And what we've successfully done and what we were trying to do is now I've taken 2 equations that I had 2 variables in each, to now I have one equation with 1 variable. I have it in 2 different spots, but it is the same variable. And now we can go on and solve for the value of b. Now we can multiply these together and get 6b cubed divided by b. What is b cubed divided by b? B squared, because one of the b's, this b on bottom will take out one of the b's on top and leave me with b squared. What can we do next? Divide both sides by 6, which tells me that b squared is equal to I believe it should be 9, because 9 times 6 is 54. If you all know that trick. 9's on your hands. 5, 6, 54. So, and last but not least, we can take the square root of both sides, which tells us that b is equal to what? Well, Square root of b squared is just b. Square root of 9 is 3. Now, we do normally add the plus or minus to it, but because, again, we covered this at the beginning, I know I've talked about this in our alternating functions, where we talked about having a negative inside those parentheses, and it ends up going positive, jumping between positive and negative because of our properties of exponentials. So this has to be positive. It has to be a positive value if we're talking about exponentials. So, well, we found the value of b. Any questions on this here? Almost. We still have to find a. Now we said a is equal to 6 over b. Well, b is 3. And 6 divided by 3 is 2. And our general equation was y equals a times b to the x. We're trying to find the equation that goes through these 2 points. So y is equal to, well, a is 2, b is 3, and it's to the x. So the general equation, the general exponential equation for this here can be written in the form of 2 times 3 to the x. Any questions on these here? Are we good with this here? Yes? All right, writing an exponential function, y equals a times b to the x, whose graph passes through the point 110 and 340. So AJ, off the top of your head, do you know what the equation would be? You know it, Charlie? Stormy, you got it? Anybody know what it is? Which is? Yep. Yeah, no, I noticed that this morning after I had printed all the copies off, that it still had been left in there. Yep, so it's actually on the note sheet. But we'll go on and find it and see how this works. Yep. Yeah, whenever you see these big white gaps, that's because I've erased the answers off of it. These are the additional problems, and they put the answer right there. So we'll use the same thing we just did. Y equals a times b to the x. So for 110, well, 10 is equal to a times b to the first, or really we can just say a times b. Our other point is going to be 40, or 3 comma 40. So when y is 40, x is 3. Now again, what we're going to want to do is solve one of these equations for a. A is equal to 10 over b. Now when I pick which one I'm going to solve for a, I always pick the one that has a smaller power of b. So here we have b to the first and b cubed. I'm going to pick the one with b to the first. It's not wrong if we wanted to solve the one with b cubed for a. It just requires us to do a little bit more manipulation of the numbers. We have to do a little bit more to solve. Now once we have this here, we can plug it in. Tells us 40 is equal to 10 divided by b times b to the third. Well, the b in the denominator of that fraction here will really cancel out with one of these here, which will just leave us with 10b squared. Because we wrote it out on the first one that we did, because we could rewrite it as 10b cubed divided by b. Well, one of those b's on top and bottom will simplify out. just leaving us with 10b squared. Now what can we do next? We can divide both sides by 10, which tells me that b squared is equal to 4, and then we would square root both sides, which tells me that b is equal to 2. We're almost done. We need to find the value of a. So a would equal to 10 divided by 2. So a is 5, which means our equation, as we saw, y is equal to 5 times 2 to the x. Any questions on any of these here? Are we ready for the next one? All right, so we're going to look at number 3. Now, hopefully you notice that this slide is a little bit different than the one you have for that one. If you notice that the middle one that you have, number 4, is at the next one also. Yeah, so when you do these, you can go from one to the next. You don't have to fill it all in that one gap. Does that make sense? Okay. Because I put them that way so that you have more space to write them, so you're not trying to cram everything into that little third of a page. Third of a half of a page, so a sixth. So let's look at this here. So looking at this here, still dealing with y equals a times b to the x. So here our y value is 2 or 12 when x is 2. Our other one we have y is 24 when x is 3. Now the process that we do for this really isn't going to change, even though we have 2 and 3 for x. So what can we do first? Solve for a. And I'll choose the one with b squared. So we can divide both sides by b squared, telling us that a is equal to 12 divided by b squared. And then we can plug it in for a. So if I multiply 12 divided by b squared by b to the third, what would we get? Well, 12b. Because the b cubed over b squared, the 2 on bottom will simplify with 2 out of the 3 on top. So 2 of these will simplify with 2 of these here, leaving me with just 1. Now what do we need to do next? Divide both sides by 12. Which tells us that b is equal to 2. So we're just missing one part. We're missing the value of a. Got to plug it back in and solve for a. A is equal to 12 over 2 squared. We can go down. Well, 2 squared is 4. And 12 divided by 4 is. So the value of a is 3. The value of b is 2. And it is to the x. Any questions on any of these here? we're going to stop here for today. We will finish this tomorrow.